Okay, yeah, hi guys, very good evening everyone. Welcome all of you once again to Om Institute and welcome to this next session on control system. Okay, yeah, so as you all know, we started, with the IIT Madras PYQ series, the IIT Madras previous year question series. Okay, the IIT Madras previously conducted the GATE examination in 2019, 2018, 2011 and 2003, of course with the 8 years of gap every time. Okay, and we are discussing control systems, all questions of EC and electrical. Okay, all questions, not not missing anything. Okay, and that is why we have split the session into two parts. Okay, the previous session Monday 3 days back we had all 1 mark questions covered, and now okay we'll have all 2 marks questions covered here. Okay, of EC and EE. Okay, related to the control systems asked in these 3 years, 2019 and 11 and 3. Okay, hope you enjoyed the previous session. Hope you have taken its PDF. Hope you have revised. And today also we'll follow the same thing. It's not only question and answer, but the question and the background behind that, some description, some explanation. Okay, and then only we go to the next question, right? Okay, related to the control systems asked in these 3 years. Okay, so yeah, that's what it is, and we will now start moving towards the questions. Okay, the audio video looked everything good to me. If there is any issue, you can let me know in the chat box here. Okay, yeah, so just a second. Okay, seems to be some problem with my pointer. Okay, but just give me a second. Okay, yeah, sorry for the interruption. Let's carry forward. Now it's working fine. Okay, yeah, otherwise it would be little inconvenient to go with the session, but yeah, now it's okay. Okay, so yeah, these were the important updates I was telling you. If you are from electrical and planning to prepare for GATE 2027 in the offline manner, so the new offline batch just started 29 July. Okay, so it's not like just yesterday the batch started, and you can enroll into it quickly. And if you're electronic students looking for new offline batch, that starts okay August 4. Okay, these are all the offline batches updates with at our Hyderabad center. Okay. Very good evening, everybody, all of you. Now let's get started. GATE 2003 EC 2 mark question. This is the first one, signal flow graph. Okay, this is a signal flow graph. Let's start with the fundamental. Topic by topic we'll go, like graphs or block diagram, or then time response errors, Routh-Hurwitz, root locus, frequency domain plots and frequency domain specifications, steady state, state space analysis, all those things. Let's move forward. Okay, so what is that I'm going to see here is, okay, first of all, we need the forward path, and forward path is any path from input to output, and then, okay, we need the loops, and then we need to build up the path factors and the graph determinant. Okay, Mason's gain formula typically will be required here to solve it, and as we know, Mason's gain formula, okay, will be given by C by R is summation Pk del K divided by delta. Okay, summation Pk del K in case of there are multiple forward paths like P1 del 1 plus P2 del 2, etc. Okay, divided by delta. So P1, P2 are nothing but the forward path gain of the kth forward path. Okay, a quick review. Delta is the graph determinant, okay, and which is equal to 1 minus sum of all the loop gains. Okay, then we take the sum of loop gain product, but product is only taken in case of non-touching loop pair. Okay, if there is a non-touching loop triplet, okay, 3 loops non-touching to each other, then we also take the loop product of that triplet as well, etc. Let's understand the loops and graph determinant with reference to this example, and then let's come to the path factor. Okay, everybody here, see this. Okay, what is the path from input to output? Input here, okay, is RS, output here is CS, and any path from input to output is the forward path. Okay, which is containing only of unit gains here. Okay, so what is the respective forward path? Okay, it is simply 1 into 1, which is equal to 1. Okay, the respective forward path gain here is only equal to 1. Okay, right, and there is only one forward path. See, at any cost you cannot go and return and come to the output, because in between you will repeat a node, and that is not allowed. When you go from input to output, none of the node in between should be repeated here. Okay, then next, okay, this is the forward path, only one forward path, but what are the loops? Okay, what are the closed loops? Okay, now very clearly you see this one loop, I'll call it as L1. Okay, which is built out of that 1 by S integrator gain multiplied by minus 2. Okay, which becomes minus 2 by S. Okay, which becomes the minus 2 by S. Okay, this is the loop number 2. Okay, L2, which is 1 by S multiplied by minus 3. It becomes minus 3 by S. Okay, it becomes minus 3 by S. Okay, right, now that's third loop that you are able to see here is 6 and 1 by S and minus 4. Okay, this will be your loop number 3. Okay, 6 into 1 by S is multiplied by minus 4. This becomes minus of 24 is divided by S. Okay, now think, are they touching or non-touching? Okay, are they touching or non-touching? So very clearly you can see that L1 and L2 are non-touching. This is L1. Okay, they don't touch anywhere. Okay, this is L2, but L1 and L3 they touch here. Okay, and L2 and L3 they touch entirely at this particular branch. Okay, so if I ask you what are non-touching here, yes, there are non-touching loop here, and that is L1 and L2. Okay, the non-touching loop here is available here, that is L1 and L2. Okay, that is L1 and L2. Okay, these two are non-touching to each other. Okay, now how will I write down the graph determinant? Okay, graph determinant, that is what I was telling you. The first term that will come is 1, and then always sum of all the loop gains. Sum of all the loop gains. So always, okay, whatever the loops are there, sum of all of them. And then if there is a non-touching pair, take the product of them. So L1 and L2 here make a non-touching pair. Okay, so take this product L1, L2. Take this product term, that is L1 and L2. Okay. Now, this tells you that the delta will be 1 minus sum of the loop gain. Sum of the loop gain means minus 2 by S, minus 3 by S, and minus 24 by S. plus product of L1, L2, 2, 3, minus minus will become plus, 2, 3 will be 6, and then 6 by S square. Overall, the graph delta is 1. All this minus minus plus, and how much total? 29. 1 plus 29 by S plus 6 by S square. Okay, 1 plus 29 by S plus 6 by S square. Okay, this is what is the delta. Okay, what next? Okay, next what is going to be the case is, okay, we have to find the delta K, the path factor of the kth forward path. By the way, only there is one forward path here. Okay, now how do we calculate that path factor? Please understand, how do we calculate the path factor? To calculate path factor, just remove the concerned forward path. Like, if you see this picture once again, okay, and if I remove, okay, just let me do that. Okay, if I remove this respective forward path, this is my forward path, na? I have erased it. The path from input to output gone. Okay, I have just simply erased it. Okay. Now you see, I will bring back what were my loops. This was my loop L1, this was my loop L2, this was my loop L3. Okay. Now, if you see, because you have erased the forward path, okay, L1 is no longer a closed loop. Okay. L1 is no longer a closed loop. It is now open, and we talk loop means a closed loop. Okay, obviously. Okay. So, path factor is known as the determinant of remaining graph. Path factor is known as the determinant of remaining graph. And how do we calculate determinant? What I told you, 1 minus sum of all the loop gains will come. Okay, so 1 minus sum of all the loop gains. Sum of all the loop gains here will be L2 plus L3. That's it. Okay, no L1. And L2 and L3 are touching, so product will not come. So product will not come. So this one will be the delta 1. Okay, and that is 1 minus, my L2 was minus 3 by S and L3 was minus 24 by S. This becomes total 1 plus of 27 divided by S. Now, we have to just apply the Mason's gain formula and write down the final answer. Okay. So, Mason's gain formula. What will be the Mason's gain formula for this problem? We will write down C by R as, only one forward path, so no summation required. It is only P1 del 1 divided by delta. By the way, P1 was 1. Delta 1 is 1 plus 27 by S. And the graph determinant we calculated as 1 plus 29 by S plus 6 by S square. Okay, multiply throughout by S square. Okay, so it will look S and 1 S I will take inside. S plus 27 divided by S square plus 29S plus 6. This is what the final answer has to come out. Okay, S into S plus 27, okay, is divided by S square plus 29S plus 6, option number D. Okay, option number D will clearly match here. Okay, everybody, option number D. Right, let's go to the next question. Here it is, GATE 2003 EE 2 marks question. Attempt this. Okay, quickly attempt this question. Right? Okay. Let's do it out. Okay, the block diagram of a control system is shown. Okay, integrator gain, what do you know? Integrator gain is 1 by S. Okay, they have written it as a block integrator. Okay, come on, if you get it parallelly, you can mention your answer in the chat box. Now see here, okay, this is integrator. Okay, that is gain 1 by S. So, you know, if you want, you can solve it using the block diagram as well. Okay, because, you know, this is going to be cascade. Okay, and then there is a overall feedback. Okay, then there is a overall feedback. Okay, you can take this, you know, separately as well if you want it. Okay, what you can do is, okay, I'll just have a slight modification here. Okay, I can remove this connection and I can take it to another summing point, and that will be in the, okay, minus form. Ultimately, what you want is this signal should be entering with the minus sign. Okay, that also you can probably do up here. Okay, so if I do those bit of you know, modifications, Okay, see, I'll take a step just for your clarity. Otherwise, you can do it directly as well. If I feed it here minus, and if I take the input here was with plus. Okay, ultimately, what was coming up here? Okay, this was input. Suppose this was x and this was y. So u minus x minus y. Ultimately, same. I have taken u minus y and then final x. Okay, it's not going to change the dynamics. Okay. Okay. So that now, what is the gain of this block? It's a simple negative feedback. Okay, g upon 1 plus gh. Okay, which will become 1 upon s plus 3. Similarly, what about the gain of this one? Okay, 1 by s, forward path gain. This is 1 by s. Okay, don't forget, integrator gain. Okay, divided by 1 plus gshs, 1 plus 12 by s. So, this one is 1 upon s plus 12. Okay, so what is the overall forward path now? Okay, if I take this as the overall forward path, what happened? If I take this as my overall forward path G, okay, that is the cascade of the first gain 1 upon s plus 3 multiplied by 2 and multiplied by 1 upon s plus 12. Okay, and then this is again the feedback path, negative sign. Okay, with the negative feedback. Okay, so overall transfer function for the system can be noted here as y upon u, and that will be equal to the overall GS is 2 upon s plus 3 s plus 12 whole divided by 1 plus GSHS again. Okay, 1 plus 2 by s plus 3 s plus 12. This is G, and the feedback gain is 9. Okay, feedback gain is 9. This is what it looks like. Okay, now when you multiply by s plus 12 throughout, you will get y by u is equal to 2 is divided by s square, okay, plus 15 s plus 3 to 36 plus 18, 54 it has to be. Okay, 2 upon s square plus 15s plus 54. Oh, by taking 27 or 18 common, they have written in the factorized form only. Okay, so no problem, we can do that as well. Okay, or I'll simplify here only. Yeah, correct. If you take this 9 and 6 LCM, you can take as 54, will cancel with 2, s plus 6, s plus 9. Okay, so if I basically create the factors here, yeah, 6 and 9, correct. This can be factorized at 2 upon 6 plus s, 6 plus 9. Okay, which will then match with option number, what I was trying to say, 6 and 9 are the factors. Now, option number B, it will match. Option number B. Okay. If you have completed, you should have got option number B, right? Okay, next question. Moving forward to the next question here. Okay, block diagram of a system is illustrated in the figure shown where xs is the input, ys is the output. What is the transfer function y by x? Okay, what is the transfer function y by x? See, first thing is that you can identify here is these two are clearly blocks in parallel. Okay, because they are fed with the same input and their outputs are respectively added. Okay, and blocks in parallel. Okay, suppose I call this gain as G. Okay, and that will be s plus 1 by s. Because when blocks are in parallel, the gains, the transfer functions are added. Okay, this will be s plus 1 by s. Okay, this is going to be s plus 1 by s. So, if you overall wanted to create a loop as well, if you just simply wanted to overall create a loop, okay, how it will look like? Okay, if I wanted to draw a simple graph here, okay, I start with x, okay, I go to this summing point, okay, then comes the gain g. For some time, I will call it as g only rather than writing s plus 1 by s. Okay, a differentiator and an integrator they have taken in parallel to each other. Okay, then this is anyway simplified as g. I come to this takeoff point. After the takeoff point, the gain is 1 by s, another integrator. Okay, then another takeoff point and then the output y. Okay, so from this takeoff point to this one, okay, there is the negative feedback, unity feedback. Okay, negative feedback, so minus gain. Okay, and unity means 1. Okay, there is one more feedback path. Okay, from the output of this G branch here. Okay, from the output of the G here again, negative feedback, unity, negative feedback. This is also minus 1. Okay, so if you wanted to count the number of loops, I am able to count that the graph has 2 loops. One is L1 and 1 I'll call this as L2. Okay, what is my L1 loop? And what is my forward path? Okay, only forward path is horizontal because these two branches are in reverse direction. So they will not contribute to the forward path. Okay, so only forward path here is, okay, this is gain 1 again into G into 1 by S into 1. So this is G by S. Okay, and what are the loops here? Loops are G into 1 by S into minus 1. Okay, so minus G by S. G we will substitute at the last. What is L2? Okay, G into minus 1. This is minus G. And L1, L2 are the two loops and they are clearly touching to each other. Okay. They are clearly touching to each other. Okay. The entire branch here is common between L1 and L2. The branch G is common to both of them. Okay. Correct now? Right. Correct. This is what is the, story. Okay. And as well as path factor. Okay. If I wanted the path factor delta 1. So see, if I erase this first forward path, see, if I erase it, what will happen? If I erase this branch goes, so L1 and L2 both open. And if L1, L2 both open, that means no more loop left. And a branch, a graph which does not have any loop, what should be its graph determinant? What is the first term you write? 1 minus sum of loop gains. Okay, there are no loops, so sum of loop gains is 0, so answer will be 1. Only answer will be 1, right? Only answer will be 1. So now I'm going to write down the answer as y divided by x. Only one forward path was there. So P1 del 1 divided by delta, and the P1 is equal to G by S. Delta 1 is 1 whole divided by graph determinant 1 minus loop gains. Both are touching, so no product term required. So minus G by S and minus G. Okay, I will multiply throughout by S. So my answer is G divided by S. Okay, divided by S here. Okay, and minus plus G and plus GS. Now substitute G. What was my G? G was actually the parallel combination of that differentiator and integrator. So this is going to become S plus 1 by S divided by S plus G, that is S plus 1 by S plus G into S. Okay, that is S plus 1 by S multiplied by S. Okay, to simplify it, I should again multiply by, I'll again multiply by S actually. Okay, so if I again multiply by one more S, I will get S square plus 1 in the numerator. Okay, and then denominator, this will be S square. Okay, this will again be S square plus 1. Okay, plus multiplied by S, so S cube. And next term will be this S cancelled, but another S I multiplied. Now, I'll just recollect the terms and write down the answer. S square plus 1, denominator cubic, highest term is S cube. S square is 2 times, so 2S square and then a S and a 1. Okay, this is what my answer has turned out to be. Okay. So S square plus 1 upon S cube plus 2S square. Okay, plus S plus 1. Option number B. Yeah. Option number B. Okay, yes, Ravi Teja. The AP AEE mock test will also start soon. Okay, will also start soon. Okay. Okay. Good evening, Srija. Right. Let's go to the next question then. Okay. Next question. Okay. Hope this was clear to you. Yeah. Very simple question. This is actually very simple, especially for 2 marks. Okay. GATE 2003 EE 2 marks. The roots of the closed loop characteristic equation of the system shown in the figure is how much? Okay. Is how much? Let's complete this. Okay. So basically, what is the characteristic equation that you normally write for any system? Is nothing but 1 plus GSHS equal to 0. Okay, so that is going to become, what is the GS? Okay, 3 upon S plus 15 in cascade with 15 upon S plus 1. Okay, HS is unity, unity feedback is given. Okay, so S plus 1, S plus 15, if I multiply, I'll get S square, 15 plus 1, 16S plus 15 plus 3, 15, 45 equal to 0. So what I am getting is S square plus 16S plus 60. Simple factors, product 60, sum 6. Product 60, sum is 16. Okay, so 6 and 10. Very easy guess. No need to apply the formula also. It is factorized as S plus 6, S plus 10 equal to 0. So what are the roots of this characteristic equation? Okay, minus 6 and minus 10. Okay, option number D. Okay, option number D. Easy one. Right? This is easy one. Okay. Good evening, Usha Rakesh. Right? Next question. Moving forward to the next question here. A second order system has the transfer function given to you. Very easy again. 2003 this question is again very easy. Okay. Spandan given the answer D. Correct only. Okay. So yeah, let's move forward. Okay, the second order system has this transfer function 4 upon S square plus 4S plus 4. Okay, what is the response of the system represented by? See, similar question we solved in the last session. Okay, only thing is differential equation was given. Okay, but similar was the question. Again, there is a direct transfer function given. You can just clearly note, okay, that what is the value of zeta from here? Okay, what is the value of zeta from here? This is 2 zeta omega n, which is equal to 4. But at the same time, what is omega n? Okay, omega n will be 2 because this is omega n square. Na? Okay, for a second order system, how do you compare the standard characteristic equation? This denominator part. S square plus 2 zeta omega n s plus omega n square equal to 0. Correct? Okay, so if I put omega n also equal to 2, okay, so 4 cancel and zeta equal to 1. So what type of waveform is expected? What is expected by a critically damped response for zeta equal to 1? Correct, Spandan? Okay, so critically damped response, which is here in front of you. This is a slower version of it. This is over damped. Critically damped and over damped becomes more slower. Critically damped is that minimum damping, okay, at which oscillations are totally cut off. Okay. For under damped, the system is still oscillatory. Option number A corresponds to zeta between 0 to 1. That is under damped. Okay. And over damped corresponds to higher damping, zeta greater than 1. And this is undamped waveform when there is no damping in the system, pure oscillatory. Okay. This happens for zeta equal to 0 when there is no damping in the system. Okay. The correct answer for the question is B here. Okay. As B here. Okay. The Spandan answer has to be B. You mentioned C. Zeta 1 you correctly mentioned, but this is not for zeta 1. This is for zeta 0. Okay. This is for the zeta 0. Zeta equal to 1 you mentioned correctly. Okay. Next one, dear. What is going to be the next question? Okay. Okay. This is still a little better. Okay. What are the natural time constants of the response? A control system with certain excitation is governed. Okay. So see, right side normally we write down the input or excitation, which is already given to you. Okay, which is already given to you, the excitation function, the input function. Okay, the response. Okay, so left side is the output term. We have to find out the xt. Okay, and talk about the natural time constant. Or not necessary to find xt, we can answer from its Laplace as well. No need to solve the entire differential equation. Correct, na? So see, first of all, if I convert this to the Laplace transform, okay, if I simply want to convert this to the Laplace transform, what is the equation given? Okay, d2x by dt square plus 1 by 2 dx by dt plus of 1 by 18 x should be equal to 10 plus 5 e raised to the power minus 4t, okay, plus 2 e raised to the power minus 5t, correct? Okay, taking the Laplace transform on both the sides, okay, s square xs, no initial values are given, okay. First derivative s into xs plus 1 by 18 xt Laplace xs is equal to 10 plus 5 e power minus 4t Laplace 1 upon s plus 4 e power minus 5t Laplace 1 upon s plus 5, e power minus 80 Laplace is 1 upon s plus a, correct na? Okay, this is what I am just using here, okay. Then what? Okay, what is going to be excess? Left side s square plus s by 2 plus 1 by 18 will be common, and right side I'll just first simplify the bit here. So I'll get s plus 4, s plus 5, and if I simplify here I'll have to multiply 10, s plus 4, s plus 5 plus, okay, here I'll have to multiply s plus 5, and here I'll have to multiply s plus 4, twice s plus 4, correct? This is what I will see. So first let's simplify the terms both the sides separately. Okay, this looks like 2s square, or rather let's take the whole denominator on the left side as 18 here, and then see what is the possible result I'm going to get. 18s square, this will become 18 by 2, 9s, and plus 1. This much is there on the left side. Okay, this much is there on the left side is equal to 10 into, okay, now s square, where are these poles going to be? That we can calculate separately also. Okay, let's simplify this. Okay, overall 10 s square plus 4 plus 5, 9 into 10, 90s. Okay, 4 into 5, 20. So this is 200, 20 into 10 plus 5s plus 25 plus 2s plus 8. Okay, is whole divided by s plus 4, s plus 5, s plus 4, s plus 5. Okay. But then I don't see any further cancellations. Maybe if I simplify numerator a bit more. Okay, what is coming till now? Okay, what is coming till now? Okay, I have excess, which is multiplied by 18s square plus 9s plus 1 whole divided by 18. This is to be equated to, now overall 10s square plus how much? 95s plus 2s, 97s. Okay, let me recheck it carefully. Yeah, 5 to 7 and 90s, correct? 97s, and constant part 225, 233. It is going then very random upon s plus 4, s plus 5, because this would be s square plus 9s plus 20 overall won't be cancelled. Okay. Just a second here. No, I think nothing is required here actually. Yeah, just I'll do one small calculation here. No guys, nothing is required here actually. Okay, let me just recalculate this once again. Okay, just a second. I'm just going to recalculate this part again. Okay, let me take up a pen here. Okay, I'll just recalculate this part and I'll match the answer here. Okay, just a second. Okay. Come back to me. See, even if I divide this on the right side, see, not a detailed calculation required, because one word, I am sorry for that, I just did not focus in the beginning itself. The natural time constant. Okay, what is natural response of the system? It is purely out of the natural response, or for that natural response anyways the excitation part would not be required. Okay, natural response, if I just go to the natural response case, okay, natural time constant they asked, okay. So all this, even if I simplify a bit and at the last if I put that condition will give me the same thing. That is what I was just manually calculating in tallying, but not required here, because I'll take the right side simply equal to 0, because I am going to talk about the natural response of the system. Okay, natural response of the system. Take the excitation function as 0. Okay, take the excitation function as 0. Okay, because see, even if I didn't do, forget this. Okay, forget this. I'll not find the initial value. What I've told you is, yeah, if I had done the correction here only, that's what the answer will be coming up only from the differential equation part. Okay, like you get the complementary function, natural response, which directly relates with the complementary function. Okay, so because if I have to go to the complementary function, I'll have to switch to mathematics. So let's solve it by control system only, S domain part. Okay, no need to simplify anything. Okay, because the answer that will turn out, okay, I just calculated CF and tallied that, okay, just for 100% clarity. Okay, but you don't have to go to any complementary function. What will you do here is XS is equal to how much? From here, if I wanted to write XS, okay, yeah, this is because of the excitation. Okay, this is because of the excitation. Let this be like this. Okay, let this be like this. Okay, divided by S square plus S by 2 plus 1 by 18. Okay, S square plus S by 2 plus 1 by 18. Now, if you focus on this one, okay, this is going to be S square plus S by 2 plus 18, 1 by 3 and 1 by 6. 1 by 3 plus 1 by 6, when you add, you get half. When you multiply, you get 1 by 18. So, I'll write it whole this way. I have some numerator function 10 plus 5 by S plus 4 plus 2 by S plus 5. Okay, divided by S plus 1 by 3, S plus 1 by 6. Okay, now tell me what are the time constant. Okay, if it is 1 plus ST form, time constant is 1 by T, or S plus A form, time constant is A. Any one case we can take. So from here, okay, what are the natural time constants? Okay, and they are going to be respectively 1 by 3 and 1 by 6. Okay, 1 by 3 and 1 by 6. That will lead to option number D. That will lead to option number D. Okay, this is what I was just telling when I calculated the whole thing with respect to the complementary function. Okay, with respect to complementary function. Okay, answer would be B here. Answer would be D here, sorry, 1 by 3 and 1 by 6. Yeah, any confusion now you can mention it to me. Right, next question. The block diagram given in the figure is a unity feedback closed loop control system. The steady state error in the response of the given system to unit step input. Okay, steady state error. Okay, for unit step input, unity feedback is given. Very good. That's what we usually want for error analysis. Okay, and now if you see the overall GS, because it is unity feedback, we can define the type of the system. See, overall forward path, these two are in cascade. So 3 into 15, 45 upon S plus 15, S plus 1. Is there any pole at origin? Okay, there is no S power n term, there is no pole at origin. Okay, so it is a type 0 case. Okay, that is why it will give steady state error due to unit step input as a finite value. Steady state error due to unit step input, what I want, as 1 upon 1 plus Kp. 1 upon 1 plus Kp, which is 1 upon 1 plus how much? So what is Kp? Okay, what is Kp? Kp is given by limit s tending to 0 gs, correct? Kp will be given by limit of s tending to 0 gs. Now when you put s tending to 0 here in the gs, okay, how much will be left? 45. Put s tending to 0, so this is 15 and 1. Okay, 45 by 15, this becomes 3. So 1 upon 1 plus Kp, Kp is 3, so net answer is 1 by 4. And 1 by 4 in percentage will become 25 percentage. Okay, 25 percentage. Yes, correct answer, Lalita. Option number A. Okay, 25% it will be. Okay, next question. Okay, the gain of the two loop position control system is given. There is a tachometer, tacho generator. Okay, derivative feedback controller basically. The gain of the tacho generator influences mainly what? Now see, if you know the conclusions of the derivative feedback controller, then also you can say the answer to this. Okay, then also you can say the answer to this, or otherwise, okay, otherwise you can, you know, still play with the characteristic equation. Okay, tachometer constant K is definitely going to affect the damping. It is going to affect the damping. In fact, it is going to increase the zeta. Okay, it is going to increase the zeta for the system. Okay, right. And if it is increasing zeta, I mean it is influencing zeta, so it will influence the peak overshoot. That is the answer to the question. Okay, that is the answer to the question. Okay, otherwise, if you take this, okay, if you take this, okay, the direct conclusion that you can remember is a tachometer controller. Okay, it affects zeta. It affects zeta. Okay, otherwise, you can take the gain of this inner loop first of all. Okay, which is G upon 1 plus GSHS, 1 upon SS plus 1 whole divided by 1 plus 1 by SS plus 1 into KS. Okay, this much. So when you multiply by SS plus 1, you will get 1 upon S plus 1 plus KS. So I will take S common, S plus 1 plus K. Okay, so now what is the final characteristic equation for the system? Final characteristic equation will be 1 plus, this is my overall forward path gain, and final feedback gain is unity. So 1 plus 1 by S plus 1 plus K. Okay, this was S plus 1 plus K. So 1 upon S plus 1 plus K equal to 0. And when you simplify, you'll get S square 1 plus into S plus 1 equal to 0, telling you that omega n will be fixed at 1 here. Okay, but zeta will depend on K. That's what I was suggesting you. Okay, zeta will depend on K. Okay, so 2 zeta omega n 1 is 1 plus K. So zeta is 1 plus K divided by 2. Okay, so it is going to affect zeta, and hence it will affect the overshoot, because the peak overshoot is given and depends only on zeta, e power minus pi, okay, into zeta divided by root 1 minus zeta square. It depends only on zeta. Okay, rather if zeta is going to increase, the overshoot is going to decrease, which is okay, good. The fluctuations reduce. Okay, so it like improves the damping in the system. Okay. The correct answer is going to be A. The correct answer is going to be A here. Okay, natural frequency of oscillation remains same. And see, because it is MCQ, one option correct. Okay, so no need to check C and D, but if you take the overall phase angle of the closed loop transfer function, that also you can see. You can find the closed loop transfer function also. Calculate the phase angle by putting S equal to j omega, and then calculate the phase angle, okay, of the closed loop transfer function. Okay, at low and high frequency, omega tending to 0, omega tending to infinity, both will be independent of K. Okay, that means this generator will not affect the what is mentioned in option number C and D, but not required. We got option number A, only one answer correct. You can move ahead to the next question. Okay, GATE 2019 EC 2 marks question. Okay, now consider a causal second order system with the transfer function 1 upon 1 plus 2s plus s square with the step response Rs equal to 1 by s as input. Let Cs be the corresponding output. The time taken by the system to reach 94%, not like 95 or 98%. It's not like a proper settling time question. 94% of the steady state value. Now, first of all, okay, this is the overall transfer function, not the forward path gain. Okay, you have to take a second order system. Okay, and this output is the output due to step input. Okay, the output is the output due to step input, and output due to step input is nothing but step response. And it's a second order question. Okay, so first of all, let us see whether that step response, okay, is like under damped or critically damped or over damped, and then decide how we can solve it. Okay, so see here. Okay, if I take the characteristic equation alone, the denominator part is s square plus 2s plus 1 equal to 0. S plus 1 whole square. Omega n will be 1. Okay, and what will be zeta? 2 zeta into omega n. Okay, this is 2. So zeta equal to 1. Critically damped. Okay, the response that is expected is critically damped. Now, always with respect to response formula also, okay, if you have followed my complete classes earlier, I always advise the students, okay, for second order system specifically, I have taken one snapshot directly from one of my previous slide, okay, so as to save time here. This much for second order, okay, what expression, what conclusion, okay, is important, this much you should always remember. Okay, it might be slightly word blurred because I've already copied from one of my existing, but it's okay, it's manageable. Okay, so see, for zeta equal to 0, like earlier one of the question I have shown you that the waveform question also, zeta equal to 0, response is undamped. The expression turns out to be 1 minus cos omega nt. System is marginally damped, oscillatory system marginally damped, and the roots are pure imaginary, plus minus j omega n. For zeta between 0 to 1, the system response is underdamped, and this is the output expression from which numerical can come. That is why I have asked you to remember it. Okay, 1 minus e power minus alpha t upon root 1 minus zeta square sine omega dt plus phi. Okay, the system is stable. Okay, and the roots are, the poles are complex conjugate lying in the LHP. Okay, which are in the form minus zeta omega n plus minus j omega n under root 1 minus zeta square, or you can also remember minus alpha plus minus j omega d, because that is what is alpha. Here in the expression also, alpha that is coming is zeta into omega n, and omega dt, this is omega d. Okay, that omega d coming is omega n into under root of 1 minus zeta square. Okay, for zeta equal to 1, this is what our current question is. The expression modifies to, this expression for zeta tending to 1 modifies to 1 minus omega, 1 minus e power minus omega nt into 1 plus omega nt. No sinusoidal part, no oscillatory. Okay, the waveform is critically damped, the system is stable, roots are real and equivalent in the LHP. In fact, for the previous question, if you thought this is s plus 1 whole square, you will say s equal to minus 1 and minus 1. Real and equal roots, left half plane is critically damped. That way also you could have commented that it is critically damped. Okay, zeta greater than 1, no need to remember any expression for output. It's based on the different zeta, we can solve using Laplace transform in such case. Okay, the response is overdamped, roots will be real and unequal, system will be stable. For any negative zeta, the system is said to be negatively damped, the response, it is unstable, and the roots will be in RHP. This much. Okay, you should always remember. So right now, because the system is critically damped, okay, what is the output expression that I will take? For critically damped, the output expression is 1 minus e power minus omega nt whole multiplied by 1 plus omega nt, where omega n is 1. You see, omega n was 1. Okay, so the output expression for the current question will be 1 minus e power minus t into 1 plus t. Okay, I am asking, okay, the time at which the output will become 94% of the steady state value. Okay, of the steady state value. The steady state value in case of whether critically damped or over damped, okay, in any of this case, okay, in the when it is oscillatory, there so we cannot define the steady state value, but in all of these cases, because it will be still oscillatory, in all of the three cases, the steady state value of the output is 1, okay, is unity, if the input is unit step. Okay, so I want the value of t at which output becomes 94%, 0.94 times the steady state value, which is 1. Okay, so that means 1 minus e power minus t, 1 plus t. Now it's a non-linear equation. This should be 0.94, or e power minus t into 1 plus t. This should be 0.06, 1 minus 0.94. It's a non-linear. It's not like a quadratic type of equation which you can start solving. Okay, so the only way here is to go with the option. Okay, you have your calculators, take option number A. Okay, 4.5. If it works out, okay, otherwise try the next one. So e power minus of 4.5, 1 plus 4.5 is equal to 5.5 times the exponential e power of minus 4.5. Let's solve this. Okay, yeah, this itself, okay, is 0.061, approximately 0.06. Okay, correct. So A itself correct, no need to move for any other option. Okay, option number A itself is the correct answer here. Option number A is the correct option here. Done? Let's move to the next question. Okay. All right, a stability regular question. The open loop transfer function of a unity feedback system is given as k upon s, s square plus s plus 2 upon into s plus 3. What is the range of k for which the system is stable? Similar question was there in the 1 mark category as well. Okay, in the 1 mark category also similar question was there. Right? Let's move ahead and check this question. Okay, so I'll first form the characteristic equation. What is going to be that characteristic equation? 1 plus GSHS, that is k by s square plus s plus 2 to be multiplied by s plus 3 equal to 0. Okay, so you will get how much? Okay, I'll multiply this whole term here, s square plus s plus 2 into s plus 3 plus k equal to 0. Let me simplify this first of all. S, then this will become s square into s cube, then s square into 3, then s into s square, then s into 3, then 2 into s, 2 into 3, 6, and then plus k is equal to 0. Okay, so now multiplying by s again, s power 4. Overall, this was s square, so s cube now. 3s, 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 total 8s, a square it becomes, plus 6s plus k equal to 0. This is my final characteristic equation. Okay, dear? This is what is my final characteristic equation. Okay, so that I will write down here, s power 4 plus s cube plus 8s square plus 6s plus k equal to 0. S power 4 and s cube. S power 4 1 and 8 and k. 1 and 8 and k, alternate these terms. Okay, s cube row 1 and 6. 1 and 6. Correct, and then 0. The s square row. Okay. In the previous 1 mark session, I have also revised a bit about Routh-Hurwitz, how to form the Routh array, that brief that I have given there also. So hope you have followed it. Otherwise, you can watch the 1 mark video as well. You can watch that 1 mark session which was conducted 3 days back. So this is going to be, now I'll reverse cross multiply 8 minus 6, 2 divided by first element of above row always. So this is going to become 2. Then 1 into k minus 0 divided by 1. So it will be k only, and then a 0. Then s power 1 row, again 2, 6, 12 minus k. Okay, so this is 12 minus k divided by 2, divided by this element. Okay, then you will write down 0 here because the entire next column 0. Column 0, determinant value 0. Last element of a row always 0. S power 0, last calculation. Suppose this is x into k minus 0. Okay, so minus 0 remove. X into k, again divide by x only. Okay, so here only k will come. This will again be 0 because the column here is 0 and last element anyway is 0. Okay, you want the system to be stable. Okay, that means you don't want any sign change or any ROZ here. Okay, you don't want any sign change, you don't want any ROZ. Okay, right, because when I told you, one thing I told you in the last class as well, same thing I will apply here. You want the system to be stable. That means no RHP root and no RHP root. Okay, means no sign change. Where? No sign change in first column of Routh array. We focus on the sign change of first column. Okay, number of sign changes in first column is the number of RHP roots, and then you also want no j omega axis roots because that makes the system oscillatory. Okay, that makes the system marginally stable, and j omega roots are possible when there are row of zeros. So I don't want a row of 0 as well. I don't want a row of 0 as well. Correct, na? Okay. I don't want row of 0 because RHP root means system will be unstable and j omega axis root system will be marginally stable, not unstable, but that will be boundary. Sometimes in the option they will take the boundary value. Okay, that is okay, but you cannot at any cost take RHP root. Okay, so that means if this is plus plus plus, I want this also to be plus, I want this also to be plus. Anyways, this has to be plus anyways from here also for necessary condition. Okay, what is necessary condition? What is necessary condition? Necessary condition says that all coefficients of the characteristic equation must be of the same sign. All coefficients must be of the same sign. Okay. So here both of them should be plus. Okay, this means 12 minus k should be positive. So k 12 greater than k is less than 12. Okay, from here directly it is k and k must be positive. So k must be positive but less than 12. Okay, k must be positive but less than 12. Oh, any calculation error happened here or what? You have to tell me in that case. Usha Rakesh says answer A. Okay, I'll just check it out once again. S square plus S plus 2, S plus 3. Okay, this was S cube and this is the typing error. This itself was 3S square. I have to change the whole thing. Anybody would have warned me earlier. Okay, this is S cube. This was 3S square. I think typing error happened that time. This is S square. This is 3S. This is 2S and this is 6. Okay, so now this is overall. Okay, 4S square. So here 4 will come. I'll have to change entirely. Okay, then this is 3 plus 2, 5S. Okay, so this will become 5S square. Okay, then 6S. That is correct. Okay, so S power 4 plus 4S cube. S power 4 plus of 4S cube. Okay, this part to better I'll remove only. Otherwise, you got the theme of solving. That is anyways okay. Okay, yeah. So rewriting the characteristic equation, S power 4 plus of 4S cube plus 5S square, correct? Plus 6S plus K. Plus 6S plus K is equal to 0. Okay, now I will start with the S power 4 row and S cube row. Okay, now this is 1 and 5 and K. 1, 5, K. And then S cube row, the alternate terms are 4 and 6 and 0. Now S square term, this is 4, 5, 20 minus 6. This is 14 is divided by 4. Okay, then 4 into K minus 0 divide by 4. This is K and this is 0. Okay, 14 by 4 I will simplify and write 7 by 2. Okay, then S power 1 row. 7 by 2 into 6. Okay, this is going to become 21. Okay, minus 4K divided by 7 by 2. This is 0. Okay, next column was 0 and last element is anyway 0. S power 0, x into k divided by x. So only k will be left and 0 and 0. Now what is going to happen? Again, all this I already told you. You have to make this positive and this gives me 21 minus 4k greater than 0. So k is less than 21 by 4. Okay, and this also must be positive. Okay, so that means k greater than 0. So k is between 0 to 21 by 4. Okay, or they have written in the reverse form. That is okay. 21 by 4 greater than k greater than 0. Okay, right? Yeah, Srija, you must have got a different equation. I agree, because there was a small typo error. I calculated 3s square, but maybe while writing it got 3s. Okay, but yeah, this is the correct answer. Option number A. Okay, option number A. If that was the characteristic equation what we have written earlier, then k is between 0 to 12. Okay, that makes it entirely a different question actually. Okay, the procedure is still the same. Okay. Okay. Let's move forward to the next question then. Okay, what is there in the next question? Again on stability, the loop gain GH of closed loop system is given by the following expression. Okay, K upon S, S plus 2, S plus 4. What is the value of K for which the system just becomes unstable? Just becomes unstable. Boundary. Okay, to find the boundary. Acha, now if you find, okay, this is only the loop gain given, GSHS. Okay. Even if I want to apply Routh-Hurwitz, I will start with characteristic equation. That will be 1 plus GSHS, 1 plus loop gain, 1 plus K upon S, S plus 2, S plus 4 equal to 0. Okay, and then this is going to become, okay, S cube plus 2, 4, 6S square plus 2 into 4, 8S plus K equal to 0. Okay, now you can go for Routh-Hurwitz. Okay, you can go for Routh-Hurwitz. Okay, we can't say Lucky, usually the IIT Madras ECEE papers have been easy, but still we can't say about 2027. Okay, you prepare everything easy, difficult, moderate. Okay, paper could be any type, your preparation should be complete. Okay, so now for this we can use the cubic shortcut. And what is that cubic shortcut? Okay, what is that cubic shortcut? Okay, when the system, okay, just becomes stable. Okay, the value of k for which the system just becomes unstable. What is that cubic shortcut actually? If I have a quick review of this. Okay, if I have a quick review of this, okay, if you write down this way, as cube plus bs square plus cs plus d equal to 0 from row theory only. Okay, but necessary condition says that all a, b, c, d must be positive, all must be of same sign. Okay, then for the system to be stable, you need, I'll call this as inner, I'll call it as outer, inner minus outer. BC minus AD must be positive. Okay, for reverse, BC minus AD negative. Okay, and for boundary, marginally stable system, BC minus AD equal to 0. Okay, BC minus AD equal to 0. So I want the value of k for which the system just becomes unstable. That means I will take the boundary case, marginally stable, BC minus AD equal to 0. That is for this question 6 into 8. This is BC, and minus 1 into 8 equal to 0, giving k is equal to 48. Okay, option number C, k equal to 48, right? And this is not a different way. This is just coming from Routh-Hurwitz, but cubic questions are very common in any type of exam. Okay, so we normally just remember this BC minus AD, inner minus outer technique. Okay, this inner minus outer technique. Done? Next question. Next question. Okay. Gate 19, 2 marks, EC. Okay. Consider a unity feedback system as shown in the figure below with an integral compensator k by s. Okay, an integral controller, or people call it as compensator as well, and the open loop transfer function gs equal to 1 upon s square plus 3s plus 2 where k is positive. The positive value of k for which exactly, okay, there are two poles, okay, for which there are exactly two poles of the unity feedback system on j omega axis. Right, Usha Rakesh, 48 correct answer for the previous one. Now you see here, first from the, it's not a question on any controller or so, it's basically a stability Routh-Hurwitz analysis still, okay, because if I write down the characteristic equation 1 plus, okay, overall forward path gain k by s cascaded with gs, and gs is 1 upon s square plus 3s plus 2, and that is equal to 0. Okay, what I am going to get is, see, s cube, okay, plus 3s square plus 2s and plus k equal to 0, correct? Okay, this is what I get. Okay, s cube plus 3s square plus 2s plus k equal to 0. Now, what is that positive value of k for which there are exactly two loops of the unity feedback system? Okay, there are overall going to be 3 roots. It's a cubic equation. Now, exactly two poles on the j omega axis. Okay, so think about the system being marginally stable. Think about the system being marginally stable, and because it is again cubic equation, what is the condition for the system to be marginally stable? Again, BC minus AD 0, because two poles means a pair of poles on j omega axis is marginally stable condition. Okay, correct. So BC minus AD 0, that is 3 into 2 minus 1 into k 0, the value of k becomes 6. Okay, the value of k is 6. NAT question it is. You can fill up the answer as 6. Right? You can fill up the answer as 6. Tell me any doubts, any type of confusion here. Answer will be 6. Okay? The final answer will be 6. Okay, next question. The root locus of the system GSHS equal to k by s, s plus 2, s plus 3 has the breakaway point located where? Okay, now breakaway point comes where? It comes between two open loop poles. Okay, see, you can solve it simply. Okay, but what are the fundamentals required to solve it? Okay, the breakaway point should always come at some point between two open loop poles on the real axis. See, breakaway points can be complex as well, but here all options are real, so I'm going for the real breakaway point. Okay, so at some point between two open loop poles on real axis, the root locus breaks away. Okay, and to obtain the breakaway point, solve dk by ds equal to 0. Solve dk by ds equal to 0. Okay, but every solution of dk by ds equal to 0 is not always a breakaway point. Okay, for it to be a breakaway point, then okay, it must lie on the root locus. Okay, it must lie on the root locus. Okay, that is, it should satisfy characteristic equation. Now, any point lying on root locus, especially real point. Okay, let us see this condition required for question or not, but just an important point. Okay, for any real point, okay, lying on root locus. So what is the existence of root locus on real axis? What is the existence of root locus on real axis? Okay, I simply call it as odd number criteria. Okay, the root locus will exist on section of real axis if the total number of poles and zeros towards the right of that section is an odd number. Okay, in the previous session also, okay, in that 1 mark question session also, we use this point somewhere. Okay, now have a look into this question first of all. What are the open loop poles? Okay, at some point between two open loop poles. Okay, open loop poles, in short, I am going to call it as OLPs. Okay, so what are the poles? Open loop poles means poles of open loop transfer function. Okay, what are my open loop poles here? S equal to 0 and minus 2 and minus 3. Okay, S equal to 0 and minus 2 and minus 3. So dear, whatever is the breakaway point, where it is expected that you should know first of all. 0 and minus 2 and minus 3. Okay, 0 and minus 2 and minus 3. Okay, it will always be between two open loop poles, but between these two or these two, on the real axis, it will be between two open loop poles. These two or these two. For that, exactly, I was telling you the odd number criteria. The root locus will exist on section of real axis if the total number of poles and zeros. I also call it as forward poles and zeros. I also simply call it as forward. When you see to the right side, forward side, you should see total odd number of poles and zeros. Total pole and zero combined, you should see odd. Total pole and zero combined, you should see odd. Okay, so see, when I see from here, how many pole and zero I see? There are no zeros, but how many pole I see? One, odd number, very good. When I see from here, how many poles and zeros I see? Sorry, I see two. 1 and 2, but 2 is an even number. I don't want even. And if I see from here, how many poles and zeros I see? Okay, 3 is the odd number. Root locus will exist here. 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 But breakaway point will come between the open loop poles. Okay. Okay, so that means one thing is clear. Minus 4 cannot be the answer, and minus 2.5 is between these two. This also cannot be the answer. Okay, so it could be minus 0.5 or minus 0.784. That is clear or not? Okay, B and C cannot be the answer. Okay, because they do not satisfy, okay, the real axis condition. Now, to exactly get the breakaway point, the first equation is dk by ds equal to 0. Okay, dk by ds means what is k first of all? Okay, we write down the characteristic equation for k. Root locus is the locus of roots of characteristic equation. Characteristic equation is 1 plus GSHS, 1 plus k upon s, s plus 2, s plus 3 is equal to 0. Okay, so what will be k here? K will be minus of this term. Okay, and if I open this term, multiply, it becomes s cube, then 2 plus 3, 5s square, plus 2, 3, 6s. Okay, now I will solve dk by ds equal to 0. Dk by ds, when I differentiate, I'll get 3s square plus 5 to 10s plus 6 equal to 0. So what are the quadratic equation? S will be minus b plus minus root over b square minus 4ac divided by 2a, 2 into 3 then. So S will be minus 10 plus minus under root of 12 to 72, 100 minus 72, 28. So under root of 28 is whole divided by the 6. Okay, is whole divided by 6, correct? Now, what are these values going to be? Let me calculate this value and write down, and this will also represent the final answer. Okay, one of them is coming out to be minus 2.548. That was the option also, and I already told you this is not going to be the answer. I already told you this is not going to be the answer. Okay, and the other one, if I calculate the other one, that is going to be minus 0.784. Okay, and this is what exactly has to be my answer. Okay, that is option number D. Rather than A, it is going to be D. Okay, correct, Lalita. Okay, answer is D here. Okay, everybody. The final answer here is option number D. Okay, then. Next question. Yeah. Root locus only, GATE 2011 EE 2 marks question. Okay. Please read this and try to answer. Okay. So, what does this question say? Let's have a look into this. The open loop transfer function GS of a unity feedback control system is given K s plus 2 by 3 upon s square s plus 2. From the root locus, it can be inferred that when K tends to positive infinity, okay, when K tends to positive infinity, okay, what will be true? Now see, when K tends to infinity means we are talking about, okay, K tends to positive infinity is about termination. Okay, because root locus is what? Root locus is the locus of roots of characteristic equation when K is varied from 0 to infinity. K is varied from 0 to infinity. Now see here, okay, for higher values of K, that means K becoming large and tending to infinity, okay, the root locus is approximated by asymptotic line. So if you think about, okay, that termination, okay, now termination, the root locus branch terminates where? Okay, the root locus branches, this is also we must know, the root locus branches terminates, okay, at open loop zeros or at infinity. Okay, at either the open loop zeros or at infinity. Okay, and for the branches which are going towards infinity, we need asymptotes. Okay, we need asymptotes. Now see here, this question, okay, what are the open loop poles? S equal to 0, 0, minus 2. Okay, repeated pole at origin and minus 2. What are the open loop zeros? Okay, open loop zeros are minus 2 by 3. Okay, so for this particular question, I will say that root locus branches starts from, okay, there are 3 branches, okay, they are going to start from, root locus branches for this case starts from 0, 0, minus 2, okay, and terminates where? Terminates at the open loop 0. Do I have an open loop 0? Yes. Okay, but 2 other branches will terminate towards infinity. Okay, will terminate towards infinity. Okay, exactly for these branches going towards infinity, I need asymptotes. Okay, how many asymptotes? Okay, 2 asymptotes because there are 2 branches going towards infinity. So I need 2 asymptotes. That is what exactly I have written here. Number of asymptotes. It is the difference between the open loop poles and open loop zeros. Okay, right. Angle of asymptotes with real axis. Okay, and intersection of asymptotes on real axis. Now, angle of asymptotes is given by 2k plus 1 by n into 180 degree, or simply remember it like this. Okay, 2k plus 1 means odd multiple. 2k plus 1 will always be odd. Odd multiples of 180 degree divided by this n, where n is the number of asymptotes. Okay, so here what is n is 2, 3 minus 1. There also I have written 2 asymptotes. N is 2. Okay, so what is the theta? okay, odd multiples of, okay, theta will be, for this question, odd multiples of 180 by 2 means 90, and odd multiples of 90 are 90 degree and 270 degree. 90 into one odd multiple, 90 into 3, and two asymptotes, so two angles I'll write. The k is 0 to n minus 1, then the values are, the number of angles required is equal to number of asymptotes. Okay, 90 and 270, or some people write it as 90 and minus 90. Minus 90 and plus 270 is equal angle. 270 anti-clockwise, 90 degree clockwise. We'll come to negative y-axis. Okay, where the asymptotes intersect on the real axis, centroid, summation poles minus summation zeros upon p minus z. Now for this question, if I copy the GS, you see here, if I take the GS here once again, k s plus 2 by 3 upon s square into s plus 2. Okay, what is going to be the centroid of the root locus will be x equal to summation, I told you, the summation of all poles minus summation of zeros divided by p minus z. Okay, summation of all the poles, 0, 0 and minus 2. These are the poles. Okay, minus the summation of zeros. 0 is at minus 2 by 3, whole divided by 3 minus 1, total number of poles minus total number of zeros. This is going to become minus 2 minus minus plus 2 by 3, okay, and divided by 2. Minus of 4 by 3 by 2 minus 2 by 3. So centroid also is at minus 2 by 3, means what? Centroid also is at minus 2 by 3. Okay, now if I mark the centroid here, okay, and what is the angle of asymptotes? Centroid is intersection of asymptotes on real axis. Okay, there are two asymptotes at 90 and 270 degree angle. Okay, intersecting on x-axis, intersecting on real axis at minus 2 by 3. This is minus 2 by 3. Okay, so from here you will draw two lines, one at 90 degree. Now this is 90 degree, correct, and another one, okay, 270, 90, 90, 90. This much, 90, 90, 90. This is 270. Okay, and these asymptotes, okay, my root locus branches will finally reach these asymptotes, okay, at infinity. So root locus branches, okay, when k tends to infinity, my branch would be coming up here, and there is symmetry, top and bottom always symmetry. Root locus is symmetric with respect to real axis. Okay, now after this much of analysis, read the question carefully. From the root locus, it can be inferred, it can be concluded that when k tends to positive infinity, three roots with nearly equal real parts exist on left half plane. Where is the third branch? Two branches are going to infinity. The third branch has anyways terminating at minus 2 by 3. Okay, third branch will anyways terminate at minus 2 by 3. That means when all the three terminate, okay, they will have real part which is nearly minus 2 by 3. One will exactly terminate minus 2 by 3. Another one will be tending towards this asymptote. Option number A. Option number A. Good conceptual question. So good for conceptual question. In fact, if you draw the complete root locus, take that as a challenge, as a homework, easy only. Okay, if you draw the complete root locus, okay, approximately how it is going to turn out for this one, I'll tell you. Okay, how the root locus will turn out for this question approximately. You will put up some efforts in breakaway points. You will not get any breakaway point. These are the, see, remember origin, but this is double pole. There are repeated poles at origin. Okay, then there is a pole at minus 2, and then there is a 0 at minus 2 by 3. Okay, what is actually going to happen is, see, one of the root locus branch will start from this minus 2 and going to terminate at minus 2 by 3, and I'll draw the arrow as well. This is the story of one of the branch, and for the rest two, I'll again bring the asymptote to the picture. This was my asymptote, correct? Two asymptotes that I have shown you in the previous one. One branch, okay, will be tending like this. There is no breakaway point that will actually come up here, okay, and one branch, okay, will approximately travel like this. If you apply the odd number criteria I told you, you will be finding that the root locus cannot exist here. because if I see to the forward side, I have two poles. It is not a single pole, it is a double pole. That is why if here you see right side even number of poles, root locus cannot exist here. So directly from this pole and this pole, this is how root locus branches will actually terminate. Okay, and this is what termination is k tending to 0. Starting is k equal to 0. Okay, from here two root locus branches started, both for k equal to 0. This termination means k tending to infinity, k tending to infinity, k tending to infinity. This is what is going to be the story of this particular root locus. Okay. You have to then tell that specific questions. You can mention as doubts to me in the telegram, Lucky. Okay, in that case, if you know the concept and what that particular question is demanding, let's you can discuss that. Yeah, we'll bring the PYQs for signal and system as well. Don't worry. Okay, don't worry. Right now, hope this question on the root locus is clear to you. Okay. Then let's see the next question. Okay. The loop transfer function of a feedback system is GSHS equal to S plus 3 upon S square S minus 3. Take the Nyquist contour in the clockwise direction. Then the Nyquist plot of GS encircles minus 1 plus J0 how? Encircles minus 1 plus J0 how? See this. Okay, encircles minus 1 plus J0 how? Now see, do you need to draw the Nyquist plot of this? Okay. Take the Nyquist contour, very clearly mentioned. I told you in the previous class, Nyquist contour direction, clockwise or anti-clockwise. Okay, that's why if you are following a subject, follow both. Okay, follow both. Okay, clockwise as well as anti-clockwise. Shrija, the topics in this session is entire control system. Whatever questions were asked, okay, in these 3 years, all 2 marks question I am covering, all. Like previous video, if you take, all 1 mark questions we have covered, but entire control system syllabus. Whatever questions were asked in this year, whether it is Nyquist, like Nyquist has come, whether it is Bode plot, whether it is state space analysis, whether it is basic transient question, steady state question, Routh-Hurwitz question, root locus question, whatever was asked. We started with signal flow graphs question. Okay. Okay. So have a look into this. Take the Nyquist contour in the clockwise direction. So previous session I told you when the Nyquist contour is in the clockwise direction, number of encirclements is given by the formula P minus Z, otherwise Z minus P. Okay, otherwise Z minus P. Now see, okay, what is P plus? Everything is I have noted in the previous sessions. I am not repeating those definitions again. P plus is the number of poles of GSHS in the RHP. Okay, first of all, what are the poles of this GSHS? What are the poles of this GSHS? 0, 0 and 3. Yes. Do you have a RHP root? Yes. Okay. So that means, okay, there is one RHP root. So P plus is 1. P plus is the number of poles of GSHS in RHP. Okay. So I got P plus. Okay. N is the number of encirclements of minus 1 comma 0 only, or minus 1 plus J0. That is correct. Okay. That is also correct. Okay. That is what we want. So people will think we have to draw the Nyquist plot. No. We don't have to draw the Nyquist plot for this question. Okay. P plus is there. What is Z plus? Okay. What is Z plus? Now Z plus means RHP, number of RHP roots of characteristic equation 1 plus GSHS equal to 0. Whereas P plus, okay, briefly I am repeating here, number of RHP roots of GSHS. Okay, N is the number of encirclement of minus 1 plus J0. So now what is Z plus? Okay, for that I have to form the characteristic equation. Characteristic equation is 1 plus GSHS. Okay, that is 1 plus S plus 3 upon S square S minus 3. Okay, equal to 0. Okay, so when I simplify this S square into S cube, then minus 3S square plus S plus 3 equal to 0. Okay, what characteristic equation I got? s cube minus 3s square, okay, plus s plus 3 equal to 0. System is definitely unstable because there is a sign change, but I want how many roots, okay, in the RHP. Okay, again going to the Routh-Hurwitz criteria. Alternate coefficients 1 and 1 here, and then minus 3 and 3 in the next row, s square row. S power 1, minus 3 again. Minus 3, minus 6 upon minus 3. Minus 6 upon minus 3, which will again become positive 2. Last element 0. S power 0. 2 into 3 by 2. This is 0. 2 into 3 by 2, 3. Okay, how many sign changes? Okay, you see here, this is plus, okay, 2 minus, 1 sign change, minus 2 plus, another sign change. This is plus 2 plus. Okay, so in first column, I told you sign changes required only in first, to be seen only in first column. 2 sign changes. Okay, 2 RHP roots. 2 RHP roots of characteristic equation. This is nothing but characteristic equation only. Okay, that means that Z plus is equal to 2. That Z plus is equal to 2. Correct? Okay, dear. Now, what is the value of n finally? So, it is more of a Routh-Hurwitz question rather than Nyquist. You should only know that Nyquist formula P minus Z. Okay, they have mentioned clockwise contour. If they mention anti-clockwise, it would go reverse also. That also I told you in my previous class. Okay. Oh, I'm so sorry. So, n is equal to how much now? P plus we saw 1, Z plus is 2, n is minus 1, and n has a sign convention. That also I told last time. Okay, minus means clockwise. Okay, minus means clockwise, anti-clockwise is taken as positive. So, this is 1 in the clockwise direction. Okay, it is encircled once in the clockwise direction. Option number A. Once in the clockwise direction. Yeah, Lucky, correct. If they are asking number of encirclement and if you can find P and Z. Okay, P we can always get from here only, na? GSHS. Z, for Z we can use Routh-Hurwitz criteria. Okay, so there are 2 different questions, Lucky. Sometimes, okay, sometimes they may give the Nyquist plot, they may not give you this function. They will directly, indirectly tell you P. Okay, they will give you Nyquist plot and then you have to see the encirclement and then they will ask Z. That is one reverse case. They will ask Z and then from Z you have to comment on stability, because for a stable system, what is Z you want? 0, na? You want Z equal to 0. Number of RHP roots 0, na? That's all. But yeah, for such type of question, okay, when you want encirclement, you know, and if the GSHS given, no need to draw the GSHS because drawing it will take time, but this is a simple thing. Okay, I'm telling you this question, if you understand the concepts more, this is more of a Routh-Hurwitz based question. Okay, with the knowledge of Nyquist formula, but you know, more calculation was about the Routh-Hurwitz. Similar questions have been there in other years also, not IIT Madras, but other years of the examination. Okay, next question. Bode plot question. We revised Bode plot in the previous session also. Okay, initial slope and all those things. Okay, the asymptotic Bode magnitude plot of a minimum phase transfer function is given. Consider the following 2 statements. The transfer function GS has 3 poles and 1 0, and at very high frequency, the phase angle is minus 3 pi by 2. One similar question we have solved in previous class also. That was only counting number of pole and 0. This is one add-on thing. Okay. Yes, correct, Lucky. Negative sign is clockwise, anti-clockwise positive. Anti-clockwise positive. Okay, then let's check it out. Date 19, electrical 2 marks question it is. Yeah. So see here, initial slope. Okay, this is minus 20 and initial slope is to be compared with minus 20n. This will tell you n equal to 1 pole. What is n? Pole at origin. So there is 1 pole at origin. Okay, now minus 20 to minus 40, the slope decreased by minus 20. At this point, slope decreased by minus 20, so this is another pole. Minus 40 to minus 60, slope again decreased, only decreased again, so this is also a pole. If the slope increased by plus 20, it will be a 0. It will be a 0. Okay, so it has total 1, 2, 3, 3 poles and 1 0 wrong. It has 3 poles correct. So overall statement number 1 is wrong. Okay, overall it has 3 poles and no 0 actually. Because if any place there was a 0, slope should have increased by plus 20. Okay, slope should increase by plus 20. Slope should have increased by plus 20. Okay, done. Okay, Lucky, you connect with me in the Telegram. You can send me a DM in Telegram. I'll guide you then regarding signal and systems as well. Okay, and then at very high frequency, the phase angle is okay. So it's already given minimum phase and minimum phase, final phase. Okay, the high frequency phase. Okay, see, remember. Okay, what is the final slope? See here. Okay, what is the final slope? If you don't see also, we have got now how many poles and how many zeros. Okay, now because the system is mentioned as minimum phase system, and for a minimum phase system, okay, final phase or also high frequency phase, okay, or phase as omega tends to infinity is given by minus 90 degree into number of open loop poles minus open loop zeros. This is the point to be used. That is minus 90 into 3 poles and no zeros. So that is minus 270 or minus 3 pi by 2. What they mentioned? The phase angle at very high frequency minus 3 pi by 2 correct. So statement number 2 is correct. 1 is false, statement number 2 is true. Option number A has to be the correct one. Option number A has to be correct one. Okay, sometimes the questions are yes around final phase. Okay, or similarly if I ask you final slope, question made on this also, final slope. Okay, final slope means again as omega tends to infinity, high frequency slope. This is given by minus 20 into P minus Z decibel per decade. Okay, but final slope formula applicable. Okay, this has nothing to do with minimum or non-minimum phase, both minimum and non-minimum phase system. This is for both minimum and non-minimum phase system. Okay. So option number A correct for this one. Yeah, GATE 2003 EC 2 marks question. Next one. Now see here, a very clear-cut analysis we'll do for this question. Okay, what is that analysis? I want the transfer function. That two options are in the non-time constant form. Okay, any first order term we write either as time constant form 1 plus st or we write s plus a. All options are s plus a. Acha. But if I just start reading this Bode plot, see, my initial slope is 0. Okay, which we write minus 20 n. N is the pole at origin. So n equal to 0 pole at origin. Sometimes initial slope may be positive also. That means zeros at origin. Okay, but right now there are no poles or 0. Nothing at origin. Okay, nothing at origin. Okay, so whenever you see initial slope 0, okay, that is minus 20 and okay, you should straight away come to the conclusion that there is no pole or 0, nothing at origin. Okay, now you see here how much is this slope. Slopes are not mentioned. Slopes are not mentioned, so we'll have to calculate the slope. Okay, we'll have to calculate the slope. What is the slope of this line? Okay, see, what is the slope of this line? Slope is height upon base or change in decibel per decade, na change in decibel magnitude. So see here, from this point to this point, to 20 to 140. Okay, so 140 minus 20. This is the change in magnitude in decibel divided by how much is the change in frequency. Now see, 0.1 to 10. Okay, and frequency, the unit of slope is decibel per decade. And what is a decade here? Decade is a factor of 10. Okay, so how many tens I have to multiply? If I do 0.1 into 10, it will be 1. I'll again do into 10, then I get 10. Okay, one factor of into 10 is decade. So how many decades of frequency? 2 decades. So this is 120 per 2. Okay, that means 60 decibel per 1 decade. Correct, na? 60 decibel per 1 decade. Okay, let's first write down all the slopes and then come to the pole and zero calculation. How much is the slope of this line now? Okay, now change in, see the change in the decibel magnitude, 160 minus 140. This is the change in decibel magnitude divided by frequency. From this point to this point, frequency 100 to 10. Sorry, 10 to 100, I'm sorry. So it is a factor of 10 into 10. Okay, so into 10 means 1 decade only. So this is 140, 160 minus 140, 20 only, 20 decibel per 1 decade. Correct. And how much is the slope here again? 0, because it is a line parallel to x-axis. Now I will write down, okay, there was initial slope 0, but here what happened? Slope becomes 60. Whenever slope increase, what I am telling you, whenever slope increase, it represents a 0 point. But slope increased by 60. 1 0 will increase it by 20. If slope increased by 60 directly, it is 3 times 20. That means this point corresponds to 3 0. Okay, there are 3 zeros at point 1. Okay, then here slope 60 became 20. Now see here, slope 60 became 20. So how much is change in slope is important. Slope decreased by 40, I can say. Slope decreased by 40 and this is again 2 times 20. So 1 time decrease by 20 is due to 1 pole. Okay, this point represents 2 poles, repeated poles at omega 10. And now here slope 20 becomes 0, that is slope decreased by 20. Here I will say slope decreased by 20 and slope decreased by 20 due to a pole. So this point is 1 pole. I can say that this point is a pole of the function, correct? This point is a pole of the function. This point is the pole of the function. Done? Okay. What else? Okay. What else? Okay. So now we have what I am able to say, that there are 3 zeros at point 1, 2 poles at 10 and 1 pole. Okay. There are 3 zeros, okay, at point 1. Okay. There are 2 poles at 10. There are 2 poles at 10 and option is ready from here only. Okay. If you see here, okay, okay, there are 3 zeros at point 1. Okay, there are 2 poles. Okay, there are 2 poles at 10 and there is a single pole at 100. Okay, at 100. Now see, wherever slope changes, that is corner frequency. Okay, what I told you last session also, when the time constant form is given 1 plus st or 1 upon 1 plus st, okay, then the corner frequency, yeah, 1 upon 1 plus st, then the corner frequency you take 1 by t. Okay, if it is s plus a term, non-time constant form, or 1 upon s plus a, whether it is pole or 0, corner frequency formula is same, and in this case it is going to be a. So I can say that if I know the omega c 0.1, the term will be, okay, from here, okay, what is the transfer function idea I have? Transfer function should contain, okay, s plus, now this is 0, 0 will be written in numerator, na? 0 will be written in numerator, 0.1, and because it is 3 zeros, so same factor 3 times, so cube, okay, then 2 poles at 10, s plus 10 square. Then there is a single pole at 100. Pole term means denominator again, so s plus 100. Okay, into some gain factor. Okay, into some constant gain factor. Okay, that is required or not, that we will decide by option. If required, we will work hard for it. Otherwise, not required. Some constant into s plus 0.1 whole cube. Okay, so now see, s plus 0.1 whole cube and s plus 10 whole square. This is available only in option number A. No need to waste your time in calculating that constant gain factor. You can take it as a homework challenge to calculate constant, because for constant we'll have to go to initial part of Bode plot, but the formulas that we apply for initial part of Bode plot to find k are those formulas when the transfer function is written in the time constant form. So you will have to write down all this in the time constant form and then solve it. That is also okay, doable, but not required for this question. So I will not touch it. Okay, not required for this question. Option number A, okay, has been matched here. There is no difficulty in solving the question without that gain factor also. Okay. The asymptotic Bode plot of the transfer function k upon 1 plus s by a, the error in phase angle and the dB gain at a frequency. Okay, now see here. Okay, I think there are some unclear data here. Magnitude plot is given, initially 20 log k, constant. Again, there are no pole at origin. That is very clear also. And this is a decreasing line. The slope should be minus 20 decibel per decade. So I hope they have just given the magnitude. That is their intent. But final slope has to be minus 20. Okay. And this is the phase angle which is starting 0. And there is a phase line given which is again negative, means minus 45 degree per decade. Okay, the intent is to calculate the error in phase angle and dB gain at a frequency of omega equal to 0.5. Error means what? Actual minus approximate. Actual minus approximate means what is the value you can obtain from Bode plot. Okay, and the difference of it from the actual result. Okay, this is my Bode plot. Which frequency I want? 0.5. Acha, this is simple here. 0.5A will be definitely below A, na? Okay, so what is the magnitude at 0.5A? Till A it is constant. So what is the magnitude here? 20 log K. Okay, because I want, okay, the error in phase angle and magnitude in dB gain error. Okay. Acha. At 0.5A, now here this is 0.1A. Let's say this is what is 0.5A. Okay, I want the phase value here. Okay, how much is this phase value? That is what I want. Magnitude was seen at 0.5. Phase I want to calculate at 0.5. Clear everybody? I want to calculate the phase at 0.5. Okay. How much will be the phase at 0.5? That is what my question. Okay. So at 0.5, now see there is a line, okay, with the slope minus 45 degree per decade. Okay. See, always what is the slope of a line formula? It is y2 minus y1 upon x2 minus x1. Okay, but in case of Bode plot, we write down phi2 minus phi1, or if it is magnitude plot, you write down m2 minus m1. Okay, but divided by x, and Bode plot x-axis is log omega always when you draw it. Okay, they have written omega value, but when we draw it on the log paper, it has to be log omega value. So we take x-axis means change in log of omega, log omega 2 minus log omega 1. Okay, so if I use this slope, some slope line is given for the phase plot, minus 45, and that is equal to this phi minus 0 using this point. See, okay, suppose this is some point B, this is some point A. Okay, I am using this line AB. Okay, I am using the slope of the line AB. Okay, which is minus 45, change in phase phi minus 0 upon change in log of frequency. Okay, log of 0.5A minus how much is the frequency here? 0.1A given, minus log of 0.1A. Okay, so this will give you phi is equal to minus 45 into, shifting this other side, log A minus log B is log A by B. So when you divide this 0.5 by 0.1, you will get 5, log 5, minus 45 log 5. We have to complete this calculation now. Okay, that is 31.45. Okay, minus 31.45. Now this is the, okay, magnitude and phase from the Bode plot, but we have to get the error. So for that I will have to calculate the actual value also. So what is the GSHS given? Okay, or I'll convert to the frequency domain directly to calculate magnitude and phase. Gj omega k upon, see what is given, k upon 1 plus s by a. So 1 plus j omega by a, 1 plus j omega by a. Now see, what is going to be the result at omega equal to 0.5a? That is the question. So when you put 0.5a, okay, directly I'll put here. So when I put omega equal to 0.5a, this becomes k divided by 1 plus j omega 0.5 a will cancel 1 plus j 0.5. Okay, now what is the magnitude of this? Okay, what is the magnitude in decibel? Okay, in decibel it is 20 log, okay, of, now what is the exact magnitude of this? K, denominator is a complex number, so root x square plus y square. We'll have to do root over x square plus y square, so root over 1 square plus 0.5 square. Okay, now this I will write 20, okay, log a by b is log a minus log b. So 20 log 5 minus 20 log under root of, this will become 1.25, 1 square plus 0.5 square. Okay, and this I'll have to calculate from calculator. Okay, this is 0.97 approximately. So magnitude is 20 log k minus 0.97. Okay, right. Whereas what is the result we got from Bode plot? Okay, from the Bode plot, my magnitude was 20 log k at this frequency. See here. Okay, at this frequency, it was 20 log k. Okay, that means how much is the error? The difference, the error is 0.97 decibel in magnitude. Okay, phase. Okay, now what is the phase of this function? Actual phase. Numerator is k, positive real number, so 0. For denominator, subtract the phase, minus tan inverse imaginary part by real part. Imaginary part by real part. So minus tan inverse 0.5, how much? Is minus 26.56. Okay, this is the actual phase obtained. Okay, but from Bode plot, how much phase I have written? Okay, just now calculated the phase from Bode plot, minus 31.45. Okay, minus 31.45 degree. Okay, so this is going to be, what is the difference in these two? That is minus 4.88 or approximately minus 4, or absolute error 4.89 degree. The difference in them, okay, the absolute difference in them is 4.89. Okay, so the error in phase angle and dB gain respectively. Okay, 4.89 approximately 4.9 and magnitude error was 0.97. So option number A will match our calculation. Option number A will be matching my calculation. Done. Yeah, let's go to this question now. The transfer function of a phase lead compensator is given to you. Okay, the frequency at which angle dj omega is maximum. Okay, the very easy question for 2 marks actually. Okay, the frequency at which the maximum phase lead of the lead compensator comes. Okay, and that frequency, okay, omega m, okay, is nothing but the geometric mean of, okay, that is under root of, okay, both the corner frequencies. And okay, what is the corner frequency for the zero term? S plus A form, corner frequency 1 by 3t. Okay, corner frequency for the pole term, suppose this is 1 and this is 2, is 1 by t here. S plus A corner frequency, okay, is A. So the answer is under root of 1 by 3t into 1 by t, geometric mean of both. And that is simple. Okay, option number C, 1 upon 3 under root 1 upon 3 t square. Option number C. Easy one for 2 marks. Okay. Then we can have the next question. Okay. State model. The ZIR, zero input response, okay, of a system by the state equation given to you. See, we had a similar discussion in the previous video as well, but the 1 mark session video, the zero input response of the system. Okay, zero input response of a system given by the state equation x dot equal to ax. So see, output equation not given. Okay, so in response means I want the state solution only. And what is xzirt? The xzirt is given by phi t multiplied by x naught. X naught is the initial state given. Okay, x naught is what is the initial state. Okay, x1 0, x2 0 given 1 0. This is what is your state transition matrix. Okay, and we had some question and discussion on state transition matrix also, right? How do we find the state transition matrix for this? Okay, this is what is the system of equation which is given as x dot equal to ax. Okay, so what is that A matrix? The A matrix for the question is 1 0 1 1. Correct? 1 0 1 and 1. Okay, 1 0 1 1. Okay, that is the A matrix. Okay, state transition matrix phi t, which is e power at, is actually given by the formula inverse Laplace of si minus a whole inverse. Inverse Laplace transform of the si minus a whole inverse. Inverse Laplace transform of si minus a whole inverse. Done? Right. Now, for that we will first form the matrix Si minus A. Okay, Si. Okay, Si identity matrix 1 0 0 1 minus the A matrix 1 0 1 1. Okay. Now, when you subtract it, this is S into 1 minus 1, S minus 1. This is 0 minus 0. Then again 0 minus 1. And then last term S minus 1 again. Okay. This is what is Si minus A. And then I need to take the inverse of this matrix first. What is Si minus A whole inverse? Now, inverse of any matrix is adjoint of the matrix divided by the determinant of the matrix. For 2 cross 2 matrix, when you take adjoint, you can simply exchange the diagonal numbers. If you don't know this technique, the basic mathematics, if you don't know, you can write down what I am telling. You can, copy my words. Diagonal numbers to be exchanged, but these are same here, so they look same. Otherwise, I have to swap them. For off diagonal number, just change the sign. So minus 0, 0. Minus 1, plus 1. Understood? Off diagonal, change the sign. For diagonal numbers, exchange these two numbers. Swap. Divided by determinant of this. Determinant, okay, anybody can write s minus 1 whole square minus 0. That is s minus 1 square only. Now, I will shift this s minus 1 square inside. I will divide with every term. Okay, so what is this si minus a whole inverse coming up here? That is, when you divide by every term, the first is 1 upon s minus 1, then 0. This is 1 upon s minus 1 square. And last term again 1 upon s minus 1. So what is my final state transition matrix? Is the inverse Laplace of this. Inverse Laplace of this. And inverse Laplace of this 1 upon s minus 1 e power t 0. Again 1 upon s minus 1 last e power t. 1 upon s minus a whole square e power at. T e power at, sorry. T e power t. These are the required inverse Laplace formula. Correct? This is state transition matrix. Okay. So final answer. X ZSRT. Sorry, ZIR. Not ZSR. X ZIRT. As I told you, state transition matrix into initial state given. Okay, state transition matrix obtained is e power t 0, t e power t and e power t multiplied by initial state, which is given as 1 0, I guess. Correct na? 1 0. Yeah, to just multiply here. Now see, first row, first column. So e power t into 1 and then 0. So e power t. Then second row, t e power t and then 0. So t e power t. This is the answer. E power t, t e power t. E power t, t e power t, option number C. That is the zero input response. Any type of doubt, you can mention it to me. Right, next question. Okay, now see, from differential equation, this is on forming the state space model. GATE 2003 EE 2 marks question. The following equation describes a separately excited DC motor in the form of differential equation. The above equation may be organized in the state space model as. Now see, normally what is the state space model we write? Okay, understand that state space model is normally arranged that, okay, we write this way: x dot equal to ax, or any matrix they can name, px plus bu or plus qu, okay, or q into va, okay, q into va. Okay, this is my input term. Okay, this is my state vector. Va is the input, x is the state vector. Okay, okay, and the state vector xt is a column vector containing all the state variables. Now you can see the system has been described by second order differential equation, means it is a second order system. And the number of state variables is always equal to the number, or is the order of differential equation. So because it is second order, it will have two state variables, x1 and x2. What are the two state variables? That is hinted to you. Okay, take the second state variable. Okay, this is going to be x2, that is omega, and take the first state variable as x1. Okay, as x1. Okay, so now please follow here carefully. Okay, so what I have been able to obtain, the first state variable is d omega by dt. Okay, and the second state variable is omega. Okay, the second state variable is omega. So I can first of all say that the first state variable is nothing but derivative of omega, and omega is x2 and will represent the derivative by dot. Okay, so x1 is x2 dot. But whenever we form state space model will never have second or any higher order equation. State space model system is arranged as only first order equations. All derivatives should be written on left side. The system is arranged as first order equation, okay, where all derivatives, okay, are arranged on the left side. So x2 dot equal to x1. Write down the derivative on left side, other thumb on the right side. Okay, now this is one relation. Okay, now differential equation is given. What is the given differential equation? That is d2 omega by dt square plus b by j d omega by dt plus k square by lj omega is equal to k by lj va, is equal to k by lj into va, right? Now see, out of this, what all we know? Okay, we know that this is my state variable x2. Okay, d omega by dt is my state variable x1. Now, what is this d2 omega by dt square? This can be written as d by dt, because I don't want any second derivative term. So let me write this way: d by dt of d omega by dt. That means this is d by dt of d omega by dt, which is your x1, and derivative of x1 is noted as x1 dot. X1 dot. So I can now read this equation and write this way. This is x1 dot plus something. So that plus something I will shift on the right side. X1 dot is equal to minus b by j x1 minus k square by lj x2 plus k by lj into va. Now I am writing both these together in front of you. X1 dot, what I have just now obtained is minus b by j x1 minus b by j x1 minus k square by lj x2 minus k square by lj x2 and plus k by lj va. Okay, and the x2 dot is equal to x1. X2 dot is equal to x1. Okay, now we have to write down this in the matrix form. Okay, I'll take left side x1 dot x2 dot, arrange in a column vector, equal to right side, okay, x1 x2, okay, plus the input coefficients. Input is va. So now see, first equation x1 dot, when you want to write, x1 should be multiplied by minus b by j, x2 should be multiplied by minus k square by lj. So that is the first row, because this first row will multiply with x1 x2 respectively, plus how much input? K by lj va. Second equation, it only depends on x1, that is directly x1. So x1 coefficient 1, there is no x2 here. so I can write it as 0 into x2, and there is no input term here, so I can write it as 0 into VA. Okay, now this is what is your P matrix, this is what is your Q matrix of the question. Okay, they can ask anything. Right now I think they asked P. What is the matrix P? Correct, na? What is that matrix P? Now see, let me read the again. Minus B by J minus K square by LJ, and then 1 and 0. Option number A. This is the procedure actually. Right. Okay, we'll plan for other years also. Right now, this is typically for the IIT Madras years. Okay, let's move ahead to the next question. Okay, now see, next question is again, okay, a question on state space model, but what we want is the damping ratio and natural frequency. Okay, 2 cross 2 matrices means second order system it is. There are two state variables. Okay, now number one is forming the transfer function. Number two, see here, there are two possible ways to think for this question. Method number one, okay, find the transfer function. Okay, right. This transfer function also has two options. There is a formula for transfer function. Okay, C into phi S into B plus D. Okay, or another way is if it is any standard form. If standard form given. Okay, if standard form given. And most commonly, if it is standard form, okay, okay, the type of questions that most regularly come to you is CCF. I will show you this is CCF model. I will show you that this is CCF model. Okay, but right now for this question, what is the method number two? Method number two is directly write down characteristic equation of system. Characteristic equation of system. And let me tell you that characteristic equation of system is equal to characteristic equation of matrix A. Is equal to characteristic equation of matrix A. Understood? Is equal to characteristic equation of matrix A. Now, what is the characteristic equation of any matrix? Characteristic equation of any matrix A is determinant of A minus lambda I equal to 0. So, from matrix itself, you can solve and complete the question. Okay, right. See, what is the A matrix? 0, 1 minus alpha and minus 2 beta. Okay, now characteristic equation, which is normally written as determinant A minus lambda equal to 0, but in control systems as well as mathematics, okay, when you talk about eigenvalue, there you need characteristic equation or Cayley-Hamilton theorem, or several places you need characteristic equation. Let me tell you, the characteristic equation for second order matrix and third order matrix should be directly written by you. For 2 cross 2 matrix, it is on solving this only. On solving this only, we write down lambda square minus trace into lambda plus determinant equal to 0. So now see here. Okay, lambda square minus trace. Trace is what? Sum of diagonal elements. Trace is sum of diagonal elements, 0 and minus 2 beta. Determinant, just cross multiply. 0 minus plus alpha. Okay, so my characteristic equation becomes lambda square plus 2 beta lambda plus alpha is 0. So what is the characteristic equation of the system? I told you characteristic equation of matrix A is equal to characteristic equation of the control system also. Okay, and that is S square plus 2 beta S plus alpha is equal to 0, telling you that omega n square is alpha. So omega n will be root alpha. They are asking zeta and omega n. Now we are done. Okay, and then 2 into zeta into omega n, which is root alpha. This is total 2 beta. 2 you cancel. Zeta value is equal to beta is divided by root alpha. Beta by root alpha. Okay, So zeta value is beta by root alpha and omega n is root alpha, taking me towards option number D as the correct one. Taking me towards option number D being the correct option. All okay now? Option number D being the correct option. Okay, fine. Okay. Now, this question, if you wanted to find transfer function, this is actually a CCF model. Okay. See, at least CCF model, before we go to this next question, this is EC 2 mark question. Okay. State space model for the second order system, CCF. Okay. CCF. I'll just brief out the CCF here. So whenever there is the transfer function B C1s plus C naught upon S square plus A1s plus A naught, the state space model turns out to be the CCF state space model. Okay, for second order system will be x dot equal to AX plus BU. This is what is a standard equation. X dot equal to AX plus BU and Y is equal to CX will come. Now A matrix first row will be 0 1. Okay, first row will be 0 1. Second row, you just look into the denominator characteristic equation part. Start with the constant part. Okay, and opposite sign you write minus A naught, then minus A1. Okay, plus 0 B. The B matrix will be 0 B. B is any constant in the numerator. Okay, Y equal to, now Y also start with the constant of numerator. Okay, constant of numerator is C naught. Okay, and then go reverse, C naught, C1. That's it. No sign change. For denominator, we take the opposite sign. Here you take the normal side, C naught, C1. Okay, normal sign as C naught, C1. Okay, that means if I wanted to write an example here, suppose you are given a transfer function something like this, 2s plus 1 upon s square plus 3s plus 5. Okay, what is the state space model? A quick review here. First row 0, 1. Okay, then minus 5, constant 5, so I write minus 5 and minus 3. This is then multiplied by x plus 0b. Any common here? No, I can write it as 1 into 2s plus 1. Okay, so that means I'll write 1 here. And y equal to cx. Okay, what is the constant of numerator? 1. Then go reverse to 1 and 2. Don't change the sign here. Similarly, if it is a third order system, okay, if you understand for third order, you can write down for fourth order also. Okay, write down the state space model. Like first row was 0. I'll rather start with the last row. Last row has the fixed pattern. Okay, start with the constant of the denominator. Okay, A naught, then reverse A1 and A2. But I told you this has to be with sign change. So minus A naught, minus A1, minus A2. Done. Okay, now see, what are the entries above? Last row you understood, na? Now, first column will be zeros only, except the last row I am telling, and here fill the identity matrix. Here you fill the identity matrix. Okay, identity matrix means 2 cross 2 identity matrix, 1 0 0 1. Okay, into X plus B matrix same 0 0 B. Only last element you have to write if there is any constant in the common in the numerator. Okay. Y equal to Cx. Tell me what will be Cx you will write. What is the Cx you will write? You will start from constant of numerator. Okay, C naught, then C1, then C2. Okay, and with same sign. Okay. So see here, there is a question directly out of this GATE 2019 EC 2 marks. Okay, what can be the A and C matrix corresponding to this transfer function? Okay, see, what is the numerator you can write? Numerator is simply 1. So you can write it as 1 into 1. Okay, 1 into 1 means the numerator constant part C naught and common part is also 1. So there is no C1, C2. Okay, there is no C1, C2. What is the A matrix I will write for this? My direct way of writing the answer. Okay, minus A naught, minus 1. My opposite sign, A naught, A1, A2, but write with opposite sign. So next minus 2. Next minus 3. So minus 1, minus 2, minus 3. Okay, then what I told you, first column 0, 0 and here you fill identity matrix. This was 0 and then identity matrix. Okay, so A matrix is ready for me and that is matching with option number A and C. Okay, now what about C matrix? C matrix, as I told you, C naught, the constant of numerator 1. Okay, there is no more term. There is no s or s square term. So that means 0, 0, 0, 0. Okay. So basically, this is what is A0, A1, A2, and this is what is C0. I already told you. There is no C1, C2. So C matrix option number A. Okay. First we got A and C correctly matches with option number A. With these techniques, you can mark the answer quickly. Okay. Otherwise, there is a whole big, conventional procedure to convert a transfer function into state space model, where you first draw the respective system, this transfer function, the block diagram or signal flow graphs are drawn, then converted to the state space model. But no, you can pretty much solve it by this method. Even for the previous question, I told you, we solved by characteristic equation. That is the good method for the previous question. But if you wanted transfer function, suppose, then no problem, I'll do that. Just as a practice, I'll do that. Okay, if I wanted transfer function, okay, I'll write down the model again. My model was x dot equal to 0, 1 and minus alpha minus 2 beta, minus alpha minus 2 beta into x plus 0 alpha into u, 0 and alpha only, na? Yeah, and y equal to 1, 0 x. Y equal to 1, 0 x. Okay, 0, 1 minus a0 minus a1. 0b, c0, c1. Very clearly, this is the CCF model given. Okay, where this will be b value. Okay, this is minus a0 minus a1 and this is c0 and c1. What will be my transfer function I told you for second order? Again, I'll write down b c1s plus c0. This was the transfer function taken upon s square plus a1s plus a0. When I fit in the value, okay, b is alpha, okay, into c1. C1 is nothing, 0. c0 is equal to 1. Okay, so only 1 will come, divided by denominator s square plus a1. What is a1? 2 beta. So plus 2 beta s. Okay, plus a0. So a0 will be alpha. Okay, so see, this is what I got characteristic equation. This is what I got characteristic equation actually. Denominator will correspond to the characteristic equation. S square plus 2 beta s. S square plus 2 beta s plus alpha. S square plus 2 beta s plus alpha. Okay guys, so we are done. We are done almost. To be very honest, just 1 or 2 questions we have missed out today, but the time is past 9:30. We'll stop here. But yeah, almost, because 2 marks questions were more in number. 1 mark we completed all, just 1 or 2 questions, especially just gain margin I could not touch. So 1 or 2 questions were only there. But gain margin and face margin we revised in the previous session. It was there. Okay. But yeah, let's stop here. Once again, quick update, guys. If you are an electrical engineering aspirant preparing for GATE 2027, and if you wanted offline batch, the highly competitive atmosphere, okay, in front of the best faculty team, live offline. Okay, the previous batch just started yesterday, 29 July. You can join to this as well. And if you are an electronics GATE 2027 aspirants, the new offline batch for you will be starting August 4. Okay, so you can plan and join this. For any queries, you can contact 9515694053. Our team will guide you. Okay, in case if you want, if you cannot come to Hyderabad right now for any reason, and if you want to learn in the live manner, online live manner, so the new batch online live also started just, okay, July 29. Okay, so you can start here and you can just one class done. You can go and watch the recording as well. Okay, so yeah, that was about the live batch. Okay, and then if you or your friends are also aspiring for the AE or AEE examination, okay, for Telangana AE AEE or for AP AEE, for the new offline batches started just 29th July. Okay, and if you or if your knowns are preparing for the upcoming AEE, AP AEE Genco Transco Discom examination, which is to be scheduled from August 22 to 28th. Okay, that is 20-25 days from now. Okay, and you can take the online crash course recorded. Okay, the AEE online crash course recorded version. Okay, for the validity of 45 days. Okay, with the fee of 9,999 and cover all your course. Okay, 30% discount for old students. Okay, so that also is a benefit you can take up from here. All right, guys. So like the previous video. Okay, like the previous session, I will share the PDF of this as well. Okay, PDF will be shared in this Telegram group. Okay, with the name mentioned. Okay, if you are not connected in my Telegram, you can connect here. This is where I will be sharing the PDF, but As a rule and a procedure, my PDFs will be password protected. I'll keep a simple password. Okay, if somebody has the first password also, they can try to guess it. I think for the first one, I kept IIT MCS1 and now I am keeping the password as IIT MCS2. IIT Madras control system 2-mark question. Okay, everything in small, IIT MCS in small followed by 2. This will be the password. Okay, the PDF will be password protection because you have watch the video, so notes can benefit you only, not anybody else, and you have shown that dedication. It's been more than 2 or 15 minutes of session, I guess, and you have been watching patiently. And those who have watched it, this is what the PDF, or those who watch it later also, they'll get the PDF. Okay, they'll get this password and the PDF will be shared in this Telegram group, as I mentioned. All right, thank you so much. Thank you for joining the session. We'll bring up this was control system 1 and 2 mark, and we'll bring up the sessions on other subjects as well. Okay, stay updated, stay subscribed. If you are not subscribed, immediately subscribe so that you don't miss any session. Bye bye, thank you, stay safe and take care of yourself.